In this lecture, first of all, we import the data that we pulled from the web in one of the previous projects, and we will also merge some data. So let's import pandas. And then we have historical stock prices for our 30 constituent stocks. And these are saved in the CSV file constituent prices. And also we make sure that we have a datetime index, and we save the data frame in the variable constituents or const. So here we have daily close prices for the 30 constituents from 2007 till 2020, end of March. And we can also get some meta information here. So in total we have over 3,300 timestamps. And actually for the company Dow Incorporated, we only have the most recent 260 prices. So this is a pretty new stock. And also for the stock ticker V, we have some missing values. And now let's go on and let's also import the prices for the Dow Jones index. And also here we create a datetime index. And let's also get some meta information. So we have no missing values here. And actually for the next lectures and for our purposes, we are only interested in the close prices. And therefore we select only the close column, but we still want to work with a data frame. So now that's the Dow Jones index data frame. Next, we can also create a merge data frame where we have prices for the 30 constituents and for the index in one data frame. And we call the data frame df, and we use pandas or pd.concat. And we pass a list with the two data frames that we created here above. And actually we concatenate both data frames horizontally, so we pass one to the axis parameter. So again, here we are starting with the constituents, and on the very right hand side we have the daily stock prices for the Dow Jones index. And still we have the column label close, so it should be better to have here Dow Jones index. And that's exactly what we are doing here. So we rename the column label close to Dow Jones index. And finally, we also have some more information on the constituents in the CSV file const.csv. And we import the CSV file and save the data frame in more info. So here we have the full company name and some more information. And with this, we have the full data here in our Jupyter Notebook. And in the next lecture, we are going to transform and slightly process the data. So thanks for watching, and see you there. Bye. In this lecture, we are going to transform and prepare our stock price data for explanatory data analysis. So in order to analyze and compare the performance of stocks, we need to create some more features. And in finance, relative price changes, also called returns, are more meaningful than absolute prices. And then having the daily returns, we can calculate the probably two most important metrics in finance, risk and mean return. So let's start and let's import matplotlib numpy, and for any figures we use the Seaborn style. Then let's simply try to plot the stock prices for all 30 constituents and the Dow Jones index in one figure. So we are creating 31 line plots. And this is actually here the Dow Jones index, and here are the 30 constituents. And obviously the Dow Jones index is on a completely different scale than the stocks. And therefore we should create a secondary y-axis with the parameter secondary y. And here we pass actually Dow Jones. And let's rerun the cell here. And now we have more or less the same scale with the secondary y-axis. And somewhere here is the Dow Jones index. But actually we can see that we do not really see anything. And you should notice that we are working here with absolute prices. And all stocks are actually starting at a different price level. And absolute prices are actually not really meaningful if you want to determine whether a stock performs well or not. And it would be more helpful to normalize all stocks to a common base value, for instance, 100. And we can do the following. So actually, we can divide each and every row by the very first row. So in the very first row, we have the starting prices for all stocks. And let's have a look what happens here. And by doing so, we are normalizing all stocks and also the Dow Jones Index to an initial value of 1. And it's actually more common to have an initial base value of 100. So we multiply each and every element here with 100. And here we have actually our normalized stock prices starting at 100. And depending on the individual performance, the stocks end at, for instance, 2,100, 149, and so on. So here we can clearly see which stocks perform well and which stocks do not perform well over our period. And now let's save here the normalized data frame and the variable norm. And let's again plot norm here. So all stocks and also the Dow Jones Index are starting at the very same base value, 100. And here we can clearly see the difference in performances. So this is actually the best performing stock, and it's Apple. And it's much better than all of the other stocks. And therefore, to compare also the other stocks, we can, in the next figure, also drop Apple and only have a look at the other stocks. So these are the normalized stock prices without Apple. And the best performing stock is obviously AXP. Then we have Boeing and so on. So this chart gives us a very first impression on the performance of stocks. But typically in finance, we use returns. And we can calculate daily returns with the percentage change method. So this is the percentage change in prices. And we create the new data frame red with the daily returns. For instance, for Apple here on the 4th of January 2007, we have a daily return of plus 2.2% and so on. And actually, we can also get some summary statistics on the returns data frame. And here we can probably see the most important metrics in finance, risk and mean returns. So first of all, this is here the mean or the average daily return. And then we have the standard deviation of daily returns, which is an indication of the risk or a metric for the risk. So this is the mean return and the risk for all stocks on a daily basis, but typically it's more intuitive to have them on an annualized basis. And now let's create a user-defined function, a summary annualized, where we can pass a data frame with daily returns, and it automatically calculates, first of all, the mean or the average daily return and the standard deviation. And then we're actually annualizing the mean and also the standard deviation, and we multiply the mean with 252. So we have on average 252 trading days in a year. And then we create here the new column return. So that's the annualized mean or average return. And then second, we have the column risk, which is actually the annualized standard deviation of daily returns. And also we drop some columns here. And let's simply define the function, and let's pass our data frame red to a summary annualized. And we save the resulting data frame in the variable summary. So here we have on the left-hand side in the index these stock tickers, and also here the Dow Jones Index. And in the first column, we have the annualized return, and in the second column, the annualized risk. And with this, we can actually compare all 30 constituents and also the Dow Jones Index in terms of risk and return. So we can evaluate the performance actually and compare the performance. But before we move on, it could be helpful to also get the corresponding company names. So we have here the ticker symbols, but probably we don't know the company name for each and every ticker symbol here. So for Microsoft, it's easy, but for others, it's actually less obvious. So let's create a left merge or a left join. And the left data frame is the summary data frame. And from the data frame more info, we actually get the ticker symbol and the company name, and we perform a left join. And actually here on the index of the summary data frame and on the ticker column of the right data frame. So let's overwrite our summary data frame. And let's set as the index the full company name. And now this summary data frame is even more helpful. So here we can see that we have Apple, American Express, Boeing, and so on. And finally, we can see here that there wasn't any company name for the Dow Jones index in the data frame more info. And therefore, we have to do this here manually. And we actually rename the row label or index label np.nan, and we replace it by Dow Jones. And now we are finally there. So this is the final summary data frame with annualized risk and return for the stocks and also for the index. And with this, we will perform an explanatory data analysis, and we are going to compare the stocks based on their performance. So thanks for watching, and see you in the next lecture. Bye. All right, in the following minutes, we are going to compare the historical performance of our stocks. And performance typically means risk and return. So from an investor's perspective, it's desirable to have a high return and a low risk, but typically you cannot have both. So in the vast majority of cases, high returns go hand in hand with high risks. And let's have a look here at our returns data frame. And here we can see that for the stock Dow or for the company Dow Incorporated, we only have the most recent 259 timestamps. And actually, the return and risk are only based on that timestamps, and that's not really meaningful to compare Dow with all of the other stocks. And therefore, we drop here Dow Incorporated and create the summary too. And here we have 29 constituents without Dow and also the Dow Jones index. And first of all, we can sort our stocks by the return from high to low. And we can visualize this with a bar plot. So let's have a look here. And here we are starting on the left-hand side with the stock with the highest return. So the return is in blue and the risk in green. And Apple has the highest return. Then we have Visa and so on. And actually, the Dow Jones index is somewhere here in the middle. And the same we can also do for the risk. So we sort the stocks by the risk from high to low, and we create a bar plot. And obviously the highest risk we have for JP Morgan, then for Goldman Sachs, American Express. So these are actually the finance stocks. And actually it's no surprise that the Dow Jones index has a fairly low risk, because it's, so to say, a portfolio with 30 stocks, and there's actually some diversification effect that reduces the overall risk, but that's beyond the scope of this project here. And third, we can also create a scatter plot where we have on the x-axis the annualized risk, and on the y-axis the annualized return. And let's remove here the company names, and let's just work with the ticker. And now we're creating a scatter plot, and on the x-axis we have the risk, and on the y-axis the return. So each and every company here is one data point in our scatter plot. And actually each point has a size of 50. And then also we are going to annotate the stock ticker to each and every point. And we can actually do this with plt.annotate. And we iterate here over the index, so over the tickers, and add the ticker to each and every data point. And this would be quite messy if we use the full company names. Therefore, we just use here the ticker symbols. So let's simply create the plot. And here we have on the x-axis the annualized risk, and on the y-axis the annualized return. And actually, again, for investors, it's desirable to be here on the upper left corner, so having a low risk and a high return. And it's less desirable to have a high risk and a low return, so being here on the lower right corner. And we could ask ourselves, is the performance of the Microsoft stock better than the performance of the McDonald's stock? And this is pretty hard to answer because Microsoft has a higher risk, but also a higher return. So this is not clear. But we could definitely say that the performance of McDonald's is better than the performance of Boeing. So here we have lower risk, but higher return. But there are actually two things that we should keep in mind, and maybe that's also beyond the scope of this course. So here we have a total risk framework, but typically in finance and investment, we are more interested in market or systematic risk. And second, our returns here are only price returns, so that change in prices. But there's also a second component for the total return. It's dividend payments, and here we actually ignore dividend payments. And for some high dividend companies, so the dividend component is an important component of the total return. So that's an important side note here, but it's not too important for our purposes and also for our index tracking. And finally, we can also calculate the correlation between the stocks. And we should definitely calculate the correlation on the returns rather than on the stock prices. So let's use the core method on the returns data frame, and let's save the correlation matrix in core matrix. And actually, the correlation coefficient indicates how well two stocks are moving together. So the values are between -1, and that means that they are perfectly negatively correlated, and +1, which means that they are perfectly positively correlated. And a correlation coefficient of 0 means that there's no relationship or correlation at all. And it's no surprise that the correlation of a stock with itself is 1. So we have this here in the diagonal. And with that many numbers, it definitely makes sense to visualize this with a Seaborn heat map. So let's import Seaborn. And again, we get here a future warning message, so we can ignore it. And we pass our data frame correlation matrix to a Seaborn heat map. And let's have a look here. And actually, we also annotate the correlation, so by passing true to the anode parameter. And actually, we scale the colors here, and we set Vmin to 0.2, so we would have a red color for a correlation of 0.2 or less than 0.2, and Vmax to 0.8, so we have dark green for all correlations that are equal or higher than 0.8. And actually, it's no surprise that all correlation factors are positive and clearly higher than 0. So typically large stocks like the Dow Jones stocks are heavily influenced by the overall state of the economy and the overall market. And therefore, they typically move together, not perfectly, but so the lowest correlation factors are around 0.3. And also, it's no surprise that the Dow Jones Index has high positive correlations with all constituents. And the simple reason is that all constituents are, of course, part of the Dow Jones Index or form the Dow Jones Index. And therefore, we have a high correlation. All right, this was explanatory data analysis, and we will continue with index tracking. Bye. All right, the plan for this and the next lectures is to track the Dow Jones Index as closely as possible with a so-called tracking portfolio of only 10 stocks. But first I want to give you some background why there's a need to track an index. So investors cannot directly invest into an index, but they can invest in a fund, for instance an ETF, that tracks the index. And the vast majority of Dow Jones ETFs just buy all 30 stocks with the respective weights. And that's not tracking, it's exactly replicating the index. And for the Dow Jones Index, this is no problem. And it can be done in a very efficient way because it's only 30 large stocks that are all very liquid, and transaction and trading costs are pretty low. But there are other indexes with thousands of stocks, and many of them are not liquid at all. So buying all stocks would be too costly. And it's definitely more efficient to track those indexes as closely as possible with a small subset, so maybe a few dozens of stocks. And you will see that the process of tracking an index is complex enough, and therefore we will focus here on the Dow Jones Index, and we try to track that index with only 10 stocks. But probably you won't do that in reality, but it works exactly in the same way for larger and more complex indexes. So in practice, there are many approaches how to select the tracking portfolio and the tracking stocks. And here in our case, we use a very simple and analytical approach. So we select those 10 stocks with the lowest individual tracking error, and you will see in a couple of minutes what the tracking error is and how we can calculate the tracking error. So what we are going to do is we try to identify the portfolio that best tracks the index in a training period. So in our case, 2017 and 2018, 2 years. And we actually fit the parameters of our portfolio to the data in the training period. And of course, this doesn't guarantee that the tracking portfolio does a good job on new data. And therefore, we need to forward test our tracking portfolio's ability to track the index. And therefore, we have a testing period, the year 2019, where we are going to forward test our tracking portfolio. Finally, regarding the length of the periods, there's no right or wrong, but typically periods should be long enough to have sufficient data and as short as possible, because a stock's or a portfolio's ability to track the index can change over time. So let's start here, and we still have saved DF. So that's the stock prices for the 30 constituents and the Dow Jones Index. And now let's only select 2017 and 2018, and let's save it in DF2. And then we create the normalized prices for that period and save it in Norm2. And we also select the daily returns for the period 2017 and 2018 and save it in Red2. Next, we need a metric that allows us to measure how well a stock or a portfolio tracks an index, and that's the so-called tracking error. And to calculate an individual stock's tracking error, we have to calculate the return differences between the stock's daily returns and the daily returns of the index. And that's exactly what we are doing here. So we subtract the returns of the Dow Jones Index from the returns of the constituents. And we save the resulting return differences data frame in red diff. So let's have a look here. And first of all, let's have a look at Dow Jones itself. So we also subtracted the returns of the Dow Jones Index from the Dow Jones Index, and it's no surprise that we get zeros here. And for all of the other stocks, of course, we have some differences on each and every timestamp. And now in the next step, we calculate the mean or the average return differences, and also the standard deviation of the return differences. And first of all, let's have a look at the Dow Jones Index. And of course, also here, the mean or the average return difference is 0, and also the standard deviation is 0. And actually, the volatility or the standard deviation of the return differences, this is the tracking error. And we try to minimize the tracking error. So first of all, in a first step, we try to identify those 10 stocks with the lowest tracking error. And we will do that in the next lecture. So hope to see you there. Bye. In the last lecture, we calculated the return differences between the stocks and the index, and we aggregated the differences and calculated the average difference and the standard deviation of differences on a daily basis. But typically it's more intuitive to have those numbers annualized. And now in the following, the plan is to put those two steps, calculating mean and the standard deviation of return differences, and annualizing them into one user-defined function, so tracking annualized. And we simply pass a data frame with the return differences to that function, and then the function calculates the mean and the standard deviation on a daily basis, and then it annualizes the average differences, and we call those annualized differences return premium, so it's either negative or positive. And then we also annualize the standard deviation, and this is then called the tracking error. So let's define the function here, and let's pass our data frame return differences to the function, and we save the resulting data frame in tracking. So here we have the average or the mean premium on an annualized basis for all stocks, and also the annualized tracking error. And again, for the Dow Jones itself, we have the value 0. And then we can also sort our stocks by the tracking error from low to high. So it's no surprise that the lowest tracking error has Dow Jones. But then here we have the 10 stocks with the lowest tracking error. And that's exactly those stocks that we will select for our tracking portfolio. So we want to track the Dow Jones index with only 10 stocks, so number of assets is 10. And let's select those 10 stocks and also the Dow Jones index with the lowest tracking errors. And let's save the tickers in the variable tracking stocks. So here we have included the Dow Jones index and those 10 stocks with the lowest tracking error. And now we can also have a look at the normalized prices of those 10 stocks and the Dow Jones index. So we select the tracking stocks in norm 2 and call this normalized tracking stocks. And we can also visualize them. And somewhere here in dark blue, we can find the Dow Jones index and the 10 tracking stocks. And finally, let's drop the Dow Jones index and let's only select our 10 stocks. And we override tracking stocks. So here we have our tracking portfolio, or actually the constituents of our portfolio. And with those 10 stocks, we try to track the Dow Jones index as closely as possible. And that's exactly what we are going to do in the next lecture. So hope to see you there. Bye. All right, we have still saved our tracking stocks. And now let's create a first simple tracking portfolio, the equal weighted portfolio. And with 10 stocks, this means that each and every stock has a weight of 10%. And we can actually create a NumPy array with 10 times 10% with np.full. So the shape is actually 10. And each and every value is 1 bit divided by 10, which is 10%. So these are the weights in an equally weighted portfolio with 10 stocks. And now we have to calculate the daily returns for the equally weighted portfolio. So first of all, we actually select only the tracking stocks and the daily returns. So here we have the 10 stocks. And actually calculating the equally weighted returns, or to say the simple average, is pretty easy. And we can actually do this with the mean method and pass 1 to the axis parameter. And by doing so, we calculate the mean for each and every row. So for each and every timestamp, we have the mean return here. But of course, this only works for an equally weighted portfolio. And that's a very special case. But we should definitely work with more general code that allows to calculate the portfolio returns for portfolios that are not equally weighted. And therefore, we can use here the dot method. So again, we are starting here with the daily returns of the 10 constituents. And now the plan is to calculate for each and every day the weighted average return. So we weight all returns by the respective weights. And we can actually do this with the dot method. And we pass the weights. So in this example, the equal weights. And it's no surprise that we get here the very same result as above. So also here we have 0.7% at the first trading day. And now let's define a function that calculates portfolio returns. So we define the function portrait. And here we can pass a weights array with 10 weights that sum up to 1. And actually then the function returns the daily portfolio returns. So actually this here. Now the target is to find a portfolio that minimizes the tracking error. So actually we have to minimize the tracking error, and let's define a function for the tracking error based on the weights. So here we can pass also the weights array. And then the function returns the annualized tracking error. So first of all, it calculates the portfolio returns, and then it subtracts the return of the Dow Jones index. So by doing so, we get here the return differences between the tracking portfolio and the Dow Jones index. And then we calculate the standard deviation. And by doing so, we get the tracking error on a daily basis. And finally, we annualize the tracking error. And now we are prepared to calculate the annualized tracking error for the equally weighted portfolio. So we pass the equal weights to the function tracking error. And we get here a tracking error, an annualized tracking error of 4.1%. And we could compare this to the individual tracking errors of the stocks. So let's have a look here. And here the lowest individual tracking errors start at 12%, 13%, and so on. So 4% is pretty good, actually. Now we have the daily returns for our portfolio, and then we can also calculate normalized prices. So we add one and we calculate the cumulative product, and by doing so we calculate actually the cumulative investment multiple for each and every timestamp. And then we want to have a base value or a starting value of 100. And actually we are starting with the second day of the year, because at the first day we want to have the value 100. So we will see this in a minute. And we save the result here in equally weighted portfolio. So the first trading day in the year 2017 is actually the 3rd of January. And here we are starting at the 4th with 100.16. And on the 3rd, we want to have actually 100. So let's copy here the normalized equally weighted portfolio to the data frame normalized tracking and create a new column, equally weighted portfolio. And we make sure that on the very first day, we are starting at a base value of 100. So here we have the Dow Jones index. And on the right-hand side, we have our equally weighted portfolio, also starting with 100. And to compare the Dow Jones index with the first tracking portfolio, it's definitely a good idea to visualize this. So we create the line plots for the equally weighted portfolio and the Dow Jones index. And here we have in blue the equally weighted portfolio that tries to track the Dow Jones index here. And it's not perfect, but it's pretty close. But of course, we will see that we can further minimize the tracking error by optimizing the weights. And that's exactly what we are going to do in the next lecture. So hope to see you there. Bye. All right, in this lecture, we are going to find the optimal tracking portfolio that minimizes the tracking error. And what we actually do, we try to find the optimal weights for the 10 stocks. And that's a pretty complex optimization, and we will use a quadratic optimization algorithm that we can find in the SciPy library. And therefore, we import scipy.optimize as SCO. And there are some constraints and bounds in our optimization that we have to take into account and that we need to define. And actually defining and running a SciPy optimization algorithm is pretty complex, and I won't go into the very details, so feel free to have a closer look on the SciPy website. And first of all, we have the following constraint. So the weights must sum up to 1, or to put it in the following equation, the sum of weights minus 1 must be 0. And we have to define this constraint in the following format. So our constraint is actually an equation, type equation, and we have the following lambda function. So the sum of weights minus 1 must be 0. So let's create the constraints here. Then next we have some bounds for our weights, and actually all weights shall be between 0 and 1, but this can be changed. So actually we do not allow short selling. And now we create 10 times a tuple with 0 and 1. So the left bound is 0 and the right bound is 1. And now with scipy.optimize, we can run an optimization based on a function that needs to be minimized. So we use here sco.minimize. And first of all, we have to pass the function to be minimized. In our case, it's the function tracking error. So we want to minimize the tracking error. And then we have to define a starting point. And the starting point of the optimization are actually the equal weights, so 10 times 10%. Then next we have to define the method. And there are quite a few methods that we can select. And here we select the quadratic optimization. And finally, we also pass our bounds and the constraint. And we actually save the results of the optimization in opts. And let's have a look here. So here we have some results. And the first output here is also the most important output. This is the tracking error, the annualized tracking error of our optimal portfolio, so 3.7%. And this is better than the tracking error of the equally weighted portfolio. And finally, here at the bottom, we have X. And here we have an array with the optimal weights. And let's get here X and let's extract here the optimal weights. And it might be best to also attach the ticker symbols. So we create here a panda series within the index, the symbols, and as values, the optimal weights. So here, for example, for Coca-Cola, we have an optimal weight of 7%. And again, we can calculate the daily returns of our optimal portfolio by passing optimal weights to the function portrait. And then we can also calculate the normalized values, starting with a base value of 100. And we save this in optimal portfolio. So on the 3rd of January, we are starting with 100. Then 1 day later, we are at 100.12 and so on. And again, we are creating an additional column optimal portfolio in the data frame norm track. And let's have a look here. So here we have, first of all, the Dow Jones index normalized. And here on the right-hand side, we have the equally weighted portfolio and the optimal portfolio. And again, it's best to visualize the portfolios. So we have the optimal portfolio that actually best tracks the Dow Jones index and the Dow Jones index. So let's have a look. And they are pretty close together. So in blue, we have the tracking portfolio, and in green, the Dow Jones index. And finally, we can further compare the optimal portfolio, the equally weighted portfolio, and the Dow Jones index. And we can calculate annualized risk and return by actually, first of all, calculating the returns and passing the returns to the function that we defined earlier, summary annualized. And here we can see for the Dow Jones index for the 2 years period, a return of 8.9%, and our optimal portfolio is pretty close. And also the risk is pretty close to the Dow Jones index. So we have an optimal portfolio here, and we actually optimized the portfolio and the parameters like the weights based on the data here. And now in the next step, we should also forward test our tracking strategy. and see how well our portfolio tracks the index also in the future. And that's exactly what we are going to do in the next 2 lectures. So thanks for watching, and see you there. Bye. All right, we have seen that our optimal portfolio closely tracks the index in the 2-year period from 2017 till 2018. But this is not a surprise, because we optimized our portfolio based on data in that period. And to use machine learning terms, we fitted the algorithm or the tracking portfolio on the training set. And actually, this doesn't say anything about how well our portfolio will track the index in the future on new data. And we should definitely test this with forward testing. And the testing period is the full year 2019. So we have still saved the data frame df with prices for all stocks and also for the index, and also the data frame returns. And we have our 10 tracking stocks. And now the plan is to automate and scale the process of calculating tracking errors and visualizing tracking portfolios and the index. So we create 2 user-defined functions. And first of all, we have the function tracking error general. And here we have some more flexibility. So we have some parameters here. We have the data parameter, and here we can actually pass a data frame with returns. Then we can pass a list with the tracking stocks, then a list or an array with the weights. And then we can also define the index that we want to track. So theoretically, we could also try to track a single stock. And then we can define the period, so the start and the end date. And what the function actually does here, it calculates and returns the annualized tracking error between the tracking stocks and their weights, and the index to be tracked in the period from start to end. So this code here isn't anything new, it's just aggregated, and feel free to go through it in more detail. And also we create the function visual, and also here we can pass a returns data frame. We can define the tracking stocks, the weights, the index that we want to track, and the start and end date. And now let's call those functions. And first of all, again, we want to calculate the annualized tracking error in the training period. So just to double check whether our code and our function works here. So we pass our returns data frame, and we pass the 10 tracking stocks, and we use the optimal weights, and we want to track the Dow Jones index. So we have to pass here the label. And the period is from 2017 till 2018. And here we get a tracking error, an annualized tracking error of 3.79%. And that's exactly the same number as we got here above with our optimization algorithm. So here. And now comes the more interesting part. So let's calculate the tracking error for the year 2019. So we actually forward test our portfolio's ability to track the index. And again, we are working with the returns data frame, the tracking stocks, and the optimal weights. And of course, again, we track the Dow Jones index. But now the period is 2019. And we save the forward tracking error in the variable forward tracking error. And it's actually no surprise that the forward tracking error is higher than actually the back testing error. So here we have 4.7%. And let's also visualize this. And still both charts closely move together, even if the tracking error is slightly higher. So we could suspect that our tracking portfolio works in the future as well, but we should definitely further analyze this. And one way how to do this is to compare our tracking portfolio with the random portfolios. And if our portfolio tracks the index better than the vast majority of random portfolios, this strongly indicates that our method to create a tracking portfolio is valid and works with new data as well. And that's exactly what we are going to do in the next lecture. So I hope to see you there. Bye. Alright, in this lecture we are going to create many random portfolios and calculate the tracking errors for these random portfolios in the year 2019. And then we are going to compare this with our optimal portfolio. And for instance, if we come to the conclusion that 50% of the random portfolios track the index more closely than our portfolio, then we shouldn't use that portfolio and try other, maybe more complex methods to create a better tracking portfolio. And actually, random portfolios mean that we select 10 random stocks, and we also generate random weights for the stocks. And first of all, let's define the bucket from which we will randomly draw 10 stocks. So we actually drop the stock DAO because we do not have the full data for the year 2019. And of course, we also drop the index, the Dow Jones index. So let's create a bucket here. So we have in total 29 stocks. And now with np.random.choice, we can actually draw random samples. And first of all, we need to pass here our bucket. And then we can define the size of the sample, so in total 10 stocks. And also we define that we want to have a random sampling without replacement. So it doesn't make any sense to have a stock twice in a sample. And therefore we pass false to the replace parameter. And let's have an example here. So these are 10 random stocks, for instance, Boeing, Disney, and some more stocks. Next, we can create 10 random weights for the stocks here that sum up to 1. And with np.random.random, first of all, we can create 10 random floats. And actually, by dividing each and every random float by the total sum, we make sure that we get actually weights that sum up to 1. So we create here random weights with 10 random weights, and let's simply make a cross check here, and let's sum up the 10 weights, and we get here 1. All right, we are best equipped to create one random portfolio, and first of all we set a so-called random seed, and here we can pass any number that we want to pass. And as long as you apply the very same random seed as I do, so for instance here 1, 2, 3, then we get the very same random portfolio. And that's why this is called pseudo-random, because by setting a random seed, we can guarantee a reproducibility of our random process. So it's still random, but it's reproducible. So let's create the random stocks and the random weights. And let's have a look here. So here we have 10 random stocks and the weights. And again, as long as you apply the very same random seed, 1, 2, 3, then you get here the very same random portfolio. Next, let's calculate the tracking error of our random portfolio here. So also in the period 2019. And here we get a tracking error of 5.5%, and compared to our optimal portfolio, this is clearly higher. And we can also visualize our random portfolio. Finally, the plan is now to create 10,000 random portfolios and calculate 10,000 tracking errors. And first of all, we create an empty NumPy array where we can store later on 10,000 tracking errors. And again, we set the random seed to 1, 2, 3. And then 10,000 times we are doing the following. So we create random weights and also random stocks. So this is a random portfolio, and then we calculate the tracking error of that random portfolio. And then we actually save the tracking error in the NumPy array. And we repeat this process 10,000 times. So we create 10,000 random portfolios. And finally, we have in the NumPy array tracking errors, 10,000 tracking errors. So let's do this. And this can take some time. And now we can calculate how many of these random portfolios end up with a tracking error lower than our tracking portfolio. So for each and every random portfolio, we check whether the tracking error is lower than the forward tracking error of our tracking portfolio. And then we take the mean to calculate the percentage. So let's have a look here. So 6.5% of the random portfolios are better than our tracking portfolio. And this is a strong indication that our tracking portfolio has some superior abilities to track the index. It's not just random. And actually, I've used the same method on indexes with thousands of stocks and a tracking portfolio size of 40 to 50 stocks. And typically less than 1% of the random portfolios perform better. So our Dow Jones example here might be too small to get more significant results. But again, 6.5% is not too bad for our small example. And finally, we can also create a histogram with the distribution of the 10,000 tracking errors. And actually, here we have a mean tracking error of around about 6%. And our tracking portfolio is here at 4.7%. So only 6.5% of all random portfolios are better. All right, thanks for watching, and see you also in the next lecture. Bye.